In chapter 5, module number 1, we shall study about another new type of derivative known as intrinsic derivative. Here we shall define intrinsic derivative of tensors and vectors, and then we shall apply into some different formulas like Serret-Frenet formulas in helix, in Burton curves, etc. We also introduce here a new coordinate system called curvilinear coordinate system. So, let us first define intrinsic derivative. Now, in module 1 of chapter 5, we shall first introduce intrinsic derivative of tensors and vectors. In section 2, we shall study about curvilinear coordinates in E3, that is space. The first, we define a curve in a space in the following way. A space curve is the totality of points whose coordinates xi satisfy equations of the form xi equal to pi I t, I equals to 1 to 3. That means, xi are the functions of t, and there are 3 functions pi 1 t, pi 2 t and pi 3 t. For study of curves by method of calculus, its parametric representation is convenient, because as t is a parameter, we can differentiate with respect to t in various ways. So, to study the geometry of the curve, its parametric representation is very important. Though it is defined with respect to t, but the natural parameter of a curve can be considered as the arc length, because arc length is invariant under the transformations. So, we can define arc length in this way: arc length from a point p0 to a variable point p on C is defined by this integration s equals to integration t0 to t root over gij dxi dt dxj dt dt. So, this formula will give us the arc length in a Riemannian space of dimension 3. Now, we come to the intrinsic derivative of a tensor, that if a tensor is of type PQ or order PQ with components A, I1, I2, IP, J1, J2, Jq, such that they are functions of a single parameter. So, we are considering here that the components are the functions of single parameter t. Then intrinsic derivative of such components with respect to t is defined by del t A I1 I2 IP J1 J2 Jq equals to A I1 I2 IP J1 J2 Jq comma k dxk dt. That means, the covariant differentiation with respect to xk has been done to A I1 I2 IP J1 J2 Jq with a product of dxk dt. So, intrinsic derivative of A I1 I2 IP and G1 J2 JQ is defined by the equation number 3. In our last chapter, we have seen how the covariant differentiation has been done. So, intrinsic derivative is again done with the help of covariant differentiation. So, comma denotes the covariant differentiation. Now, let us see for a contravariant vector how the intrinsic derivative will come out. So, del ai del t can be written as ai comma k dxk dt. That means, ai comma k is the covariant differentiation of ai with respect to xk. And we know the expression of ai comma k is del ai by del xk plus a m gamma I m k with the product of dxk dt. Now, from the theory of partial derivatives, the first term of the right hand side will come to dai dt plus am gamma I m k dxk dt. So, equation number 4 is the intrinsic derivative of contravariant vector whose components are ai. Similarly, intrinsic derivative of a covariant vector whose components are a lower I can be expressed in equation number 5, that is del ai del t equals to dai dt minus am gamma m I k dxk dt. So, we can see that for contravariant vector there is coming a plus sign, but for the covariant vector is coming a minus sign. Let us think about the intrinsic derivative of the fundamental tensors and Kronecker delta, and we can prove that they are all 0. Proof is very elegant. Del g I j del t can be written as g I j comma k dxk dt, and from the previous chapters Ricci's theorem, we know that g I j comma k is equal to 0. That is, the fundamental tensors are covariantly constant. So, applying that result, it follows directly that del g I j del t is equal to 0. In a similar manner, the other results will also follow. Now, another very simple result, that the intrinsic derivative of an invariant, that means a scalar function, coincides with its total derivatives. So, del phi del t, we want to know the expression of del phi del t, and by definition we can write del phi del t equals to phi comma k dxk dt, and we know from covariant differentiation of invariants that phi comma k is nothing but the partial derivative of phi with respect to x to the power k. So, we can write del phi del x k dx k dt, and from the theory of partial derivatives that can be expressed as d phi dt. So, del phi del t is equal to d phi dt. That means, the intrinsic derivative of an invariant is equal to its total derivative. Thus, the intrinsic derivative is the generalization of ordinary differentiation, where we differentiate with respect to one parameter, and covariant derivative is the generalization of partial derivative. Now, let us introduce a new coordinate system named curvilinear coordinate system in space. As the space are not flat, so we need a new type of coordinate system, and its name is curvilinear coordinate system. Now, suppose x1, x2, x3 be three quantities related to the rectangular Cartesian coordinates of a point P, y1, y2, y3. So, at first we are taking a point P whose Cartesian coordinates are y1, y2 and y3, and we are relating this y1, y2, y3 by some functions, and we denote them as x1, x2, x3. So, we can write this expression yi equals to phi I x1, x2, x3, where I is running from 1 to 3. That means, y1 equals to phi 1 x2, x3, x3, y2 equals to phi 2 x1, x2, x3, and y3 equal to phi 3 x1, x2, x3. So, three functions are there, and we have to assume that phi i's must be independent such that the Jacobian will not vanish. That means, del y1, y2, y3 by del x1, x2, x3 will not equal to 0. To exist the inverse transformation, we need this condition. Under these conditions, we can get x1, x2, x3 as a single valued function of y1, y2, y3 with continuous partial derivatives of the first order. So, inverse transformation exists for this type of equation. So, we can attach a coordinate system P x1, x2, x3 with respect to P y1, y2, y3. Such a coordinate system is called curvilinear coordinate system of the point P. Now, let us explain the fact given by the equations earlier. Now, if I consider x1 equal to c1, where c1 is a constant, and let x2, x3 be allowed to vary, then we can write the equation as yi equal to phi I c1 x2 x3, and we know that the functions of two variables will represent a surface. So, this one will represent a surface. Similarly, for x2 equal to c2, where c2 is constant, and here x1, x3 will vary, and again x3 equal to constant c3 and x1, x2 will vary, will also give 2 more surfaces. So, there are 3 surfaces coming out when you are considering x1 equals to constant, x2 equals to constant and x3 equals to constant. Now, these surfaces are called coordinate surfaces. Next, we consider 2 constants at a time, that x1 equal to c1 and x2 equal to c2. Then the equation will reduce to this form, yi equals to phi I c1 c2 x3, and it is a function of a single variable x3, and we know that function of a single variable will represent a curve. So, it will represent a curve known as x3 curve. Similarly, we can consider x2 equals to constant and x3 equals to constant, and it will be denoted by x1 curve, and the other curve is denoted by x2 curve. So, such curves are denoted by xi equal to ci, and they are called coordinate curves or parametric curves. Now, these curves, which are called the coordinate curves, and P is the point of intersection of these curves with coordinates x1, x2, x3, and this one is called curvilinear coordinates of P. So, P has now 2 type of representation. One for Cartesian coordinate system, it is denoted by y1, y2, y3, and at the same position, if we consider that P is lying on the intersection of 3 curves, x1 curve, x2 curve and x3 curve. So, it has a point with coordinates x1, x2, x3 also, which is the curvilinear coordinates of P. Now, let us see 2 examples of this new type of system, that is curvilinear coordinate system: spherical polar and cylindrical polar coordinate system, where y1 equals to x1 sin x2 cos x3, y2 equals to x1 sin x2 sin x3 and y3 equals to x1 cos x2. So, this is the 3 functions, that is the transformation rule from Cartesian coordinate system to polar spherical coordinate system, and this x1, x2, x3 will frame a curvilinear coordinate system on sphere. Similarly, y1 equals to x1 cos x2, y2 equals to x1 sin x2 and y3 equals to x3. For these transformations on cylinder, x1, x2, x3 will frame a curvilinear coordinate system on a cylinder. Now, let us see an example where we can observe that the equation of sphere is quite different when it is expressed in spherical coordinate system than in rectangular Cartesian coordinate system. Let us see the example. Now, from the transformation rule for spherical to Cartesian coordinate system, we have x1 equal to root over y1 square plus y2 square plus y3 square. This is coming from the equation represented just earlier. X2 is coming to cos inverse y3 by root over y1 square plus y2 square plus y3 square. And so, if we put x1 equals to 4x2, the values obtained above, and simplifying, we get that it represents y1 square plus y2 square plus y3 minus 2 whole square equal to 4, which is a sphere in Cartesian coordinate system. Its equation is this one, and it is a sphere with center 0, 0, 2 and radius 2. So, when a sphere is represented in Cartesian coordinate system with this equation, it can be represented in spherical coordinate system with the above equation x1 equal to 4 cos x2. Now, let us see the line element of E3 in curvilinear coordinate system is given by ds square equal to gij dxi dxj. In our earlier chapters, we have obtained this expression. This is the metric in Riemannian space. So, we can use this distance formula here also for the curvilinear coordinate system, where Gmn is equal to del x bar I, del xm, del x bar j, del xn, g bar ij, where G is the covariant tensor of rank 2. Now, if ds1 denote the line element along the x1 curve, that means ds1 is the arc length along x1 curve, we can write ds1 square equal to g11 dx1 square, because the other dx2 and dx3 will be equal to 0. So, ds1 square will be equal to g11 dx1 square. Similarly, ds2 square equals to g22 dx2 square and ds3 square equal to g33 dx3 square. So, in module 1 of chapter 5, we have learned two new things. In section 1, we have learned about the intrinsic derivative of tensors and vectors. It is a new derivative and it is the generalization of total differentiation. In the second section, we have introduced a new type of coordinate system in space known as curvilinear coordinate system. These will be applicable in our next modules and in next sections. So, we end this module of chapter 5 with these two sections.